So here we plug in the information. P is the gauge pressure that is given in this problem is 1 psi, so 1000 psi. And then R, I remind you, R is the interior, the inner radius. So for this one here, we are given the outer diameter is 21 divided by 2. That is the outer diameter, the outer radius divided by minus sigma minus the thickness. The thickness is 0.5. So this should be 10. Okay. So here I emphasize in class the R should be the inner radius, and T is the 0.5 inch. So plug in here, then you should be able to calculate sigma 1 should be 20 ksi. This one is 10 ksi. Okay. So here I really want to emphasize, so if you have the mistake here, and I take the 5 points off. For the second one, we want to calculate the stress normal to the welding. And so for this case, you can see right now we, for example, we take the elements like this, and the element, and this is the hoop stress is 20. This is the longitudinal stress is 10. And the welding is the 30 degrees counterclockwise. So here, this is our welding orientations. So for this case, this is the welding condition that we're looking for is what is the normal stress, normal to the welding surface. So that is in this orientation we're looking for. Okay, so in this way we calculate is this is a stress element. For example, here is X, this is Y. So this is X prime, Y prime. So here we're interested along the welding surface, that is the Y prime surface. So either you take up the formula, for example, for here, the given one, sigma X equal to 20, sigma Y equal to 10, and then here for theta equal to 30 degrees because these are counterclockwise, so that is the positive. Either you pick up the 3 values into calculations to calculate what is the sigma Y prime, and then what is the tau X prime Y prime. The 2 values will give you the answer. Or otherwise, we can take up the Moore circle. For the Moore circle, here we allocate the point. Here is X prime point, has the coordinate 20 and 0. So here, this is our X point, 20, 0. And here is the Y prime, so that is 10, 0. So this is a Y plane, and that is 10, 0. So for this Moore circle, it's centered at 15, and it has the radius equal to 5. Okay, and now again, we rotate counterclockwise 60 degrees, the 30 degrees, so on the Moore circle is 60 degrees. So we rotate into here. So that is, we rotate by 2 beta angle. So that is, this is X prime, this is Y prime. So right now we already identify, we here for the information on the welding surface, that is corresponding to the Y prime plane. So here we have to look for what is the coordinate for Y prime. So this will be our sigma normal to the welding. And this will be the tau, and again that is on the welding. Okay, so with those information we plug into tau like this, and then we work on the coordinate. So this is 60 degrees. So we can on the things, for example, using this triangle here, you can quickly figure out this distance is 2.5. So this distance from here to here is 2.5. Basically here, let me draw that one. So this is a triangle we use. So this is 60 degrees, and the radius R is 5. So this is 2.5, and this is 2.5 times. This is R times sine 60 degrees. Okay. So from here you can see the distance here is how much? 10 plus 2.5, or you can take 15 minus 2.5, so that is 12.5. Okay, and then for this one, that is you can calculate this one, that value is equal to 4.43. So therefore, on the welding surface, we have information the normal stress is equal to 12.5. And then this one is the strain stress. Strain stress has this orientation. So on the y plane, that strain stress should be pointing to that direction, because that has a tendency to rotate the stress cube, the stress element about the center by in this sense. Okay, so this is 4.43, and both unit is KSI. And here for the grading, if you are unsuccessfully to identify the sigma y prime, this is the plane, the sigma y prime is what we're looking for, and then I take the 5 points off. And if you kind of mix use the sigma x prime, then basically I will ask you which one, because sometimes some of you kind of providing sigma x prime and sigma y prime two values for me to choose from. So basically you give me a test. So I put a question mark there. Okay, I ask you which one, and that is this one here. And for the directions of the strain stress, I take the 5 points off. And if you have any calculation mistake on the magnitude of this value, and again 5 points off. Okay, and now with this in place, and we're looking for what is the maximum strain stress in the thickness in the tank of the wall, in the wall of the tank. So from here, you simply, if you answer the maximum is R, this is the maximum, and that is not enough, because that gives us the, we call the in-plane. So actually, if you remember that one using the out-of-plane information, or we put into the 3D, so actually the maximum should be corresponding to, if we connect from the tangent to the origin to here, so that should be this radius. So this is our maximum, and this maximum occurred in the out-of-plane orientations. And in one lecture, I draw these the cubic. I draw the cubic, and then in this one, in that sections, I show you there's a one kind of the diagonal plane, and that is what we call the autoplane for this case. Okay, so the maximum is not in the plane of the welding, but is kind of orientated in this way. In that case, the maximum is equal to 10. Okay, this problem is a little bit tricky, and
can you calculate that out with equations too?
Yes, for those equations that can only provide us is based upon the rotation of this in-plane. Okay, that equation only valid for rotating. For example, if this is a cube, we look at in this orientation. Equation can only apply to the orientation about this. But right now, this green one about the orientation change of the direction is in this way. So equation only valid for the rotation transformation in this sense. But right now for this case is in this sense.
So we have to use the Moore circle?
Have to use more circle. Yeah. Okay, I never show you.
No, not that big circle.
Not that big circle. I think there's a one lectures we have talked about this one. I can dig out from the YouTube. Right now we have YouTube. I can show you. Okay, but this one, I didn't take off too many points, but that is the one for see if you really have the thorough operation for this test. And if you answer this value, then basically I only take 2 points off. So the reason why for this problem I didn't put too many points here, but I want to see how many of you can get it. For the second one, any questions about this? for the second one,
I just have a quick question. So
Yes.
whenever we're talking about stressing with the walls, then we'll be out of plane stress. Is that kind of the idea?
for this one, when we start with this one, this is our welding. So this is our given starting point. And then we rotate it into here. This is our welding plane. So for given those kind of x, y, in this way, we call this the in-plane. In-plane, that means based on which we start with our two-dimensional analysis.
Oh, okay.
Is it possible for you to like overall give us what the answers were? Like, what were the final answers for each of these problems?
I didn't get it. The
Like-
final.
Like, what were the correct values for each of the steps?
Oh, you're saying will I be able to provide you the solution?
Yeah.
Would that be the solution here?
Well, no, I mean, well, the thing is, you didn't like give us numbers. Like, you showed the procedure, but I'm asking for the actual numbers calculated.
Yes. So for example, that's 10.
No, yeah, that was T max, but then
Yes.
like
And
those like
say tau
Sigma.
equal to 4.43, right? So tau and
okay.
sigma, that's being obtained from the calculation here.
oh okay,
already.
okay, never mind.
Okay. For the second one, and here let me draw the x, y, z, and then this is k, this is h. And then here we have the loading. Let me schematic draw this one. So the loading is applied in the x parallel to the x directions. So this is 10 kilonewtons. Let me call that is p. And the distance here we given is few hundred millimeter. And from here to here, that is 150 millimeters. So for this one, the first question asking what is the distribution of the reaction force and moment or torque on this cross section. That is always the first step. So for this case, we can say that is the, let me draw the cross section here. So this is the x, y, and z. So this is point H, this is point K. So to calculate the first one, we fix the reaction force first. The P is applied 10 kilonewtons, so that means on this sections we have, in the x direction, we have the force, reaction force, parallel to the cross section. So that means here we use V. And that in magnitude, in equilibrium, equal to 10 kilonewtons. And now we fix the moment. So allow me to use the moment using this equation, R times F. So here, what is R? R is the distance, the position vectors from the origin that is fixed on the cross-section we're interested to where the loading is applied. So that is our vector R. Okay, so for this case, we put into this matrix here. So that is using in terms of the IZK corner systems. And from here, if you read the R carefully, R is in, has no component in X. So here is 0. And then has Y component 0.15, and I transform into in terms of the meter. And then in the K component, it has 0.2. Okay, and then we fix the F, the direction, the vectors of the force. The P is a force applied in the X direction only. So this is 10 kilonewton, and this is unit, and then 0, 0. Okay, so for this case, we can extend it. So for I, we take this pivot and then take away those things, so multiply the things, and this will be 0. and then we plus j. So again, we use j as the pivot, and take away this row and this column. So we multiply this one 10 times 0.2. And then we, for the k, and take away the row and column. So k will be equal to minus 10 times 0.15. Okay, so here is our j component is 2. So this is our k component is minus 1.5. So we put those information onto the drawing here. For the j component, the moment about the j, which means about the y-axis, which is 2, positive 2. Our thumb aligned to the positive y direction. So positive 2, that would be in this all circulations. So in this circulation from here, you can see that is rotating about y. So in this way, the moment we calculate here, apply to this problem, that is actually is a torque. Okay, so here we convert it into the physical meaning. So here is 2 kilonewton meter. And now for K, in the K component, that is minus 1.5. Because of minus, we align our thumb to the negative z. The circulation gives us the magnitude. So here, that is mz equal to 1.5. Again, this is a magnitude in the direction of negative k. So align to the negative k, and that is a circulation, and that is 1.5. Okay, so here that is the for preparing these problems. And because this is the part of the homework, so if you couldn't get a number right, I couldn't give you any partial points. Okay, assume that you have exercise. So now with everything ready, we can proceed. So at the point H, you have calculated at K as a part of the homework. So right now we calculate H. At point H, we have the loading, and we have the normal stress and shear stress. In the loading, we have V. And from V is 10, so here is 0, and this is VQ over IT. And for this case, we can see this is a cross section, and V is applied to here. So this is our neutral axis, and point H is here. Okay, so from here you can see this one we have to calculate the VQ over IT. So now the V equal to 10 kilonewtons. And what is Q? For this case, this is the hollow shaft or hollow tube. So here that is the cross sections we've been focusing on. So Q will be equal to the area I provide you this formula here. So this is a semicircle, and the distance here is how much? That one equal to 2r square. No, how much?
You're looking for a central?
I don't have one in my.
I think it's 4 over 3 pi.
4r over 3 pi. Thank you. So for this case, that would be equivalent to this one. So therefore, for this case, Q equal to 4r over 3 pi times the square, the half of the pi, the area. So this one will be equal to 3 2r squared. So that is a formula. So right now, for this case, we're calculating is using the minus this one. Okay, we're using this one because here we only interested is in the outside, in the outer ring of this case. So basically that's the 2r. Let me call the outer radius is r, and then the inner radius is ri. So that would be 2r cubed 3 minus 2 Ri cubed over 3.